thing we'll do before we get into calculus proper is to do a little review of pre-calculus so that we're all on the same page as we continue. So that's why this first unit is called Functions, a review of pre-calculus. And first we'll look at the beginning idea of a function and start with the definition of a function. So, the idea before I write down the definition is the following. And I'm hoping you've seen this before so that this will be a reminder. Remember how functions can be schematically drawn. If this x is a value that goes into a function, we often write functions like this. We say this f represents the function, it takes a value x and produces a value we call f of x. This f of x is referred to as the image of x under f, and sometimes the x is referred to as the argument that results in this image. There are other visualizations we can use, and I'll put a few of them here. You can think of x going into a function machine, and the function machine might look something like this. It's got an input and an output. It's called f and produces the value f of x. So you can think of a function as a machine that takes in a value and produces a value. That's fine too. You can also use the words input and output, where function here in the middle might be, if you like, a computer program, and it produces an output. Finally, we often say x goes into the function f and produces a letter y. If we don't want to remind ourselves that this came from the function f, we sometimes use the letter y. In that case, we'll say that x is the independent variable. That's the variable that is unaffected yet by the function. It's the one that starts the process. And then y, which is the result of the function acting on x, we call the dependent variable, because it depends on what x is. And that seems to make good sense. So with that in mind as a reminder of the idea, let us go ahead and write down the proper definition of a function and use that from here on. So a function, f, is a rule of some kind that has to satisfy a certain property. Is a rule that associates with each input, using that notation, with each input, a unique, and by unique, of course, we mean exactly one. So we associate with each input a unique or exactly one output. This is the crucial definition of a function, input to output. Each input gives you exactly one output. Now, if the input is written, as it often is, if it is written, say, x, then the output is written, as you saw on the other page, as f of x. And we write it this way so that we remember that it's f acting upon x. This is not a multiplication, of course, and let me write that down so we're clear on this. This is not a multiplication. This is not a multiplication of f times x. This is rather the function f acting upon x, and this symbol representing what comes out of that process, the output. Another way to say that is, so, the function itself is represented perhaps by something like this. F of, and a box goes here, and this is where the input goes. The input goes into here. So f of this empty box is a way of representing the function also. Now functions can be given to you in several different ways. A function can be represented, and represented can mean described or visualized in several different forms. And here are some of them that you'll see often in practice. One is it can be represented as a table of values. Secondly, it can be represented as a graph, and we'll talk more about this a little later. It can also be represented as a formula, an algebraic formula, which is a very familiar way for many students to remember functions, but it's not the only one, as you can see here. Also, it can be represented in words. We can describe what the function does without using any symbols. These are all equally legitimate ways of representing a function. Although formulas is what you see most often, please be aware that the other ways are legitimate and will be used in different circumstances. In each case, just to reiterate, in each case a function must be absolutely predictable. Absolutely predictable. And what I mean by that is just another way of saying the definition. An input, say x, always has exactly the same, or how about this, exactly one and the same output, f of x. It doesn't matter when you do it, the function will always produce the same output for this given input x. It will never change. That is the key idea to what makes a function different from other sorts of relations. Finally, let me say a word about notation here, just to see it in operation. A function might be given, for example here, as this polynomial 3x squared minus 4x plus 2. This is an example of a function given by a formula. We might also write y equals 3x squared minus 4x plus 2. Using y instead of f of x is not quite as informative, doesn't tell us what the name of the function is, but very often we use this when we want to graph functions, which we'll talk about later. When we want to evaluate a function at a point, say evaluating f at minus 1, this is the notation we use for that. We put the minus 1 in where the x was. And then that means everywhere there is an x, we substitute minus 1. So this becomes 3 times minus 1 squared, minus 4 times minus 1 plus 2. Now all of that will add up to 9. What we then have is this input, which is minus 1, leading to this output, which is 9, by the action of the function. And sometimes we put these two together in the form of an ordered pair, and that will lead us directly into our next topic, which is the graphs of functions. Now that we've looked at the notion of a function, let's look at how to visualize a function in the form of what you know as graphs. Let me first begin by giving you some examples here of a number of graphs of functions that you may be familiar with. Here's the function y equals x squared. Here is another function, which is the y equals x function, the line through the origin. Here is another function that will become very important for us. It has the vertical line in the center is what we call an asymptote, and this is the function y equal 1 over x. And here perhaps is another example where it starts at the origin and goes off to the right like this. This is the function y equal the square root of x, which we can also write as x to the 1/2. These are each examples of the graphs of functions, the way we visualize functions most commonly, and they're very, very handy. Notice that in all of these pictures, each x value was what we previously called an input. Each x value is associated with exactly one y value. And that was what we previously called an output. For example, if we have an x value here in the x squared picture, there is exactly one y value here associated with it. And that's, of course, because when you graph, you have x squared as the coordinates of that point. So you need an x value and the y value. X squared, of course, is y here. The same thing for all these others. If we pick an x value, notice that above it, there's only one y value. Above this previous x value, there's only a single y value. Anywhere along this function, there's exactly one y value above it. Here, there's exactly one, or sometimes, if we pick an x over here, there is no y value. This is a feature of all functions and leads to a graphical test for whether or not a picture is the graph of a function. This is called the vertical line test, and it's a test for the graph of a function to see whether a curve in the plane is in fact the graph of a function. So this is the vertical line test for the graph of a function. And it is an if and only if statement. Goes like this. a curve in the xy plane is the graph of a function of some function, say we'll call it f, that is true if and only if, we use a double arrow here, I'll come back and mark that in a second, if and only if no vertical line intersects, no vertical line, that is, intersects the curve more than once. So that means a vertical line could intersect a curve either not at all, which is 0 times, or once, but not more than once. And that's the key to the pictures we saw on the previous page. Here are some examples of curves in the plane that are very familiar, but which are not the graphs of functions. This is a circle. Unit circle, say, centered at the origin. This is not the graph of a function. Why? Because vertical lines in many places cross the curve. In this one, in this case, crosses the curve twice. So that's not allowed. A vertical line must only intersect the curve once. So these are not the graphs of functions. And let me give you a second one. If you just take something like this, you have something that is a perfectly good curve in the plane and may be useful at some later date, but does not represent a function as we have defined it. Now, let us look at some examples of functions that are going to be useful to us. First of all, we have a handy function. This is called the absolute value function. And we will be using this many times for many purposes. The function is defined this way. F of x, we'll call it, which is the absolute value function. There's the absolute value notation. And we will define this in 3 parts. It is equal to x itself if x is a positive number, x is greater than 0. It is equal to 0 if x is equal to 0. And it is equal to minus x if x is less than 0. That is to say when x is negative. The graph of this function is one that's very well known. It's simply a 45-degree V with its nose down here at the origin. So this would be a line where the slope is equal to 1, and this line here on the left would be one whose slope is equal to minus 1. This is the point origin, the origin point here, and the features of this curve are that if you have a point 2 here and a point minus 2, their absolute values are identically the same. The absolute value of 2 and minus 2 is exactly equal to 2, and you can see this in this graph. A couple of other notes about the absolute value function. It is helpful to note that algebraically, the absolute value function allows you to write the square root of x squared as a single object, the absolute value of x. Because when you square a number, remember the minus sign is removed, it is gone, it's destroyed, and then when you take the square root of that positive number, you only recapture the positive square root, which means this number, whatever it is, will always be positive, and that will be the absolute value of x. That's very, very handy in calculations. Lastly, let me point out something that students need to be aware of. Here I have written minus x. Be careful. Minus x is not negative here, because x is less than 0. X is negative, so minus x is in fact positive, which is what the absolute value should produce. In general, when you see a negative in front of a variable expression, you have no idea whether that expression is positive or whether it's negative. You have to know something about the variable. In this case, we do. But in most cases, you should find out before you assume that this is a negative number. In addition to the absolute value function, functions of other sorts can also be defined in pieces. Now, these come up often enough and are called piecewise defined functions that we ought to take a look at one. So here's an example. F of x equals, and we'll define this in 3 parts, so 3 pieces. First part, it will be 0 if x is less than or equal to minus 1, we'll define it to be 1 minus x squared if x is caught between minus 1 and 1, and we'll define it to be x if x is greater than or equal to 1, writing it in that fashion. This part of this expression here defines the domain of f, and that's how these piecewise functions are organized. The domain is here. This is the functional value on those domain strips. And I will explain what I mean by strips in a moment, but you see the function is divided up into parts that are less than minus 1, between minus 1 and 1, and greater than minus 1. That means when we look at a picture of the function, if we mark minus 1 here and 1 here and draw vertical dotted lines, what we see is that the plane is divided up into 1, 2, 3 big strips. And on each strip the function is different. On the strip for x less than or equal to minus 1, the function is 0. So it's 0 here, going off to the left forever. We'll skip the middle one for a moment and look at the one at the other end. If x is greater than or equal to 1, the function is x. So let's see. At 1, x would be a height of 1 and go off at this 45-degree direction. Now, what about the part in the middle? Well, to remind you of something, let's look at what this is derived from. Recall that this is from the unit circle. And here's how. The original unit circle is x squared plus y squared equal 1. That's the equation of the full unit circle. If we solve this for y, you'll find that you get y is equal to plus or minus the square root of 1 minus x squared. The plus or minus indicate either the upper semicircle or the lower semicircle. So by choosing the plus version, which is what we have up here, we have the upper semicircle. And the reason that we need to distinguish the two is that the semicircles individually are graphs of functions, but the circle itself, as we saw, is not the graph of a function. So that graph will be a graph that looks like this with an open hole at this end, because the function is at 1 is defined to be x up here, which is 1, which is this point. There's no hole, there's a hole there, so there's no point there. And there's also a hole here, but you can't see it because it's filled by the 0 from the previous part of the function. Now this function is fully defined, and what we have here are, as I said, 3 vertical strips. And that's the way to think about drawing piecewise defined functions. Next, we'll look at what are called the domain and range of functions. Remember the image I had of a function before, that x goes to f of x via the function f. If you look at the set of all possible x's, so we write that out as the set of all allowable, and that will be determined by the function, the set of all allowable inputs, and you put them all together, that is called the domain of f. So all the numbers that can be allowed into the function is called the domain of the function. And likewise, the set of all these f of x's, the set of all resulting outputs, that is to say outputs that result from these allowable inputs, the set of all resulting outputs is what we call the range of, and this is the domain of f, this is the range of f. There we go. Now most of the time we will be concentrating on the domain because that determines what values the function is allowed to operate on, and the range is just what comes out. We sometimes will look at the range, but the domain will be more important for us. And very often we will not even mention the domain of a function, so we need to address that issue. If no domain is mentioned, which often happens, we will make the following assumption. We will always assume the largest possible domain. That's what we always do so that we don't have to keep writing down domains for every function. We'll always assume the largest possible domain called the natural domain of the function f. So the natural domain of a function is simply the largest possible set of allowable values that the function will act upon. Let's look at some examples. Find in all of these the natural domain. Now this is a good exercise and something you want to keep in mind as you work with functions. Don't start thinking of functions, especially when they're given as formulas, as just algebraic expressions to be manipulated. Remember, there's a domain involved and you have to be clear on what that is. F of x equals x cubed. In this case, the domain of f, and here I'll abbreviate domain of f by writing DOM, nice convenient abbreviation. The domain of f is all real numbers. And sometimes that's written with a boldface R, because any number can be cubed. There's no restriction whatsoever here. If we look, however, at this function, f of x equals, say, 1 over x minus 1 times x minus 3, in this case, the domain of this function is all real numbers except two numbers, except 1 and 3. And the reason is, if you put in 1 or 3 here, you'd get division by 0. So those numbers have to be left out. They are not allowable in this function. Therefore, the domain of this function can be written as the union of these intervals from minus infinity to 1 open, union 1 to 3 open, and then union 3 to infinity open. That's the way we would illustrate this with the symbols of intervals. If you wanted to illustrate this with a number line, you could. You might have a picture that looks something like this. Here's 1, here's 3. They are open holes, so they're not included, but everything else on the real number line is included. Finally, for examples, let's take this one a little bit more complicated looking. X squared minus 5x plus 6 under the square root symbol. Now you may already notice that that can be factored, so I'm going to go ahead and do that. X minus 3 times x minus 2. And let's examine the domain of this function. Now here in the previous one, what could go wrong? What could go wrong is division by 0. In the square root situation, what could go wrong is if there were a negative number under the square root. The square root of a negative number would lead us to a complex number, which we won't be examining in calculus. So this has to be non-negative underneath the square root symbol. So domain of f will be all real numbers, except for some that we'll eliminate here. All real numbers where the underneath part, which is originally x squared minus 5x plus 6, wherever that is greater than or equal to 0. Now what you should do here, and this is a good algebraic exercise, is verify this calculation, which leads to the domain being minus infinity to 2 including 2, union 3 including 3 to infinity. And you can draw a number line picture, but it's going to be everything here from 2 to the left and everything here from 3 to the right, if you like. So verify this calculation for practice, but these are examples of domains, natural domains for very familiar functions. So let's summarize the usual reasons to restrict a domain. These are things you want to keep in mind. The usual reasons to restrict a domain. The first one we've already seen is avoid division by 0. That is not allowed, so we must make sure that that can't happen. We also want to avoid, a little more generally, even roots of negative numbers. Now our example was only the square root, but any even root would have the same difficulty. Finally, here is another reason to restrict a domain. We might be working in an applied problem in which there are restrictions, physical restrictions, that the problem imposes. So we might need to meet the conditions of an applied problem. For example, in an applied problem, you might be working with a length or an area. Those numbers have to be 0 or positive. They can never be negative. Also in a problem, you might have minimum or maximum values that are determined by the physical situation. You can't go larger or smaller than a certain number because of something happening in the problem. That would be a restriction that we can't mathematically define, but you'll have to get from reading the problem. The other two are very easy to observe, these mathematical restrictions. Division by zero, you just look in the quotient. Avoiding even roots of negative numbers is also straightforward. So keep these in mind as you look at domains. Now for a couple of exercises. The first one is the following. Compare the natural domains of the following two functions. F of x equals x squared plus x over x plus 1, and g of x, the other function, which is just the function x. Give those a try. Something to be aware of in finding the natural domains of these functions and then comparing them. Let's see what we have. First thing is, let us observe in the first function, f of x. Certainly you see that there's an x in both of the terms of the top, and so you would be tempted to factor that out, and you should. So if I write this as x squared plus x over x plus 1, I can factor an x out of the top and get x times x plus 1 over x plus 1. Now, this is where you have to be careful. The naive student might say, well, x plus 1 over x plus 1 is 1, and I will remove that so that f of x becomes x, which is the same as g of x, and then conclude that the two functions have the same natural domain. But that would not be correct. The reason is x plus 1 has a variable in it. Because it has a variable, it might possibly be 0 sometime. And if it's ever 0, dividing 0 over 0 is not going to give you 1. And of course, it is 0 in one case. It is 0 when x is equal to minus 1. So what happens? In fact, the function x has two parts. It's equal to x if x is not equal to minus 1. If you don't have minus 1 for x, then this cancellation is indeed correct. However, if x does equal minus 1, the function f is undefined. It has no value whatsoever, which means the domain of the function f is equal to everything in the real numbers except minus 1. So you could write it this way as two open intervals, or you could draw it this way in the number line as this is minus 1. It is everything except that number. That is different from the domain of g, which is all real numbers, no gaps, because you could put minus 1 in here and get back minus 1, no difficulty. So this is a warning to be careful when you have quotients and not to cancel without thinking. For a second problem, let's look at one that's a bit more elaborate and takes a bit of time to write out. And it is a nice long word problem, you might say, that will allow you to think about several things. So here we go. A company has adjoined a 1,000 foot squared rectangular enclosure, so think of a yard or a pen, enclosure to its building. Okay, we are told that three sides of the enclosure are fenced in. All right. Then there is the side of the building that butts up against this enclosure. So the side of the building, say, adjacent to the enclosure, this pen that we are creating, is 100 feet long. And the enclosure may not be 100 feet long itself, so we'll write down that a portion of this side of the building is used as the fourth side of the enclosure. Okay. Let x and y be the dimensions of the enclosure. And since there are two possibilities, let's just set this where x is parallel to the building. And finally, let's let the letter L, capital L, be the length of the fencing we need, of the fencing required. Now, I haven't even gotten to the question yet. This is just writing down the situation. A company has adjoined a 1,000-foot squared rectangular enclosure to its building. 3 sides of the enclosure are fenced in. The side of the building adjacent to the enclosure is 100 feet long, and a portion of this side is used as the 4th side of the enclosure. Let's call the dimensions of the enclosure x and y, where x is measured parallel to the building. Let L be the length of the fencing required. Now here are your questions. Question A, find a formula for L in terms of x and y. Second question, B, find a formula for L in terms of x only, not x and y, just x. Final question, what is the domain of the function that you write down in part B? So there are your 3 questions. It's time for you to do a little work on this problem. Here are the 3 questions you were asked to answer. Find a formula for L in terms of x and y. Find a formula for L in terms of x. And then what is the domain of the function in part B, which will depend on the circumstances of this problem. So let's take a look at what kind of an answer we can come up with. Well, the first thing you should do is draw a picture. Now, I know that the side of the building is 100 feet long. So I'll write this down this way, 100 feet, and I'll write side of building. I don't know anything else about the building, so I probably shouldn't draw anything else. Then I know I have this rectangular enclosure here of some kind butting up against the building. So here's the enclosure. I'm told to label the part that is parallel to the building by X, and then the other part by Y. And notice that both pieces here are the same length, so I'll mark Y on both sides. I also have this piece of information that the area of the enclosure is 1,000 feet squared. Okay, well, let's see if we can answer our questions. L is the length of the fencing around this enclosure, and we want to write this in terms of X and Y. Well, we just need to look here. We see we have X and 2 Y's, so X plus 2Y does the trick. Part B, we want to write the same L, the length of the fencing, but we don't want to use Y. So we'll have X plus 2, and now I need to find some other expression for Y, which means I need to go back here and say, is there some information here that would allow me to write X and Y in terms of one another? Well, here's a piece of information we haven't used yet, the fact that the area is 1,000 foot squared. Now, the area of a rectangle is defined to be the product of the 2 sides, which would be xy in this case. Xy, of course, is given to be 1,000. So there we are. We can write y as 1,000 over x, and then substitute that down here and get 1,000 over x. So now we have L written in terms totally of x. Finally, we want to find out what the domain of L is. Well, before I write anything down here, let's make a few remarks. First of all, x cannot be 0. Why would that be? Well, look up here. X times y has to be 1,000. If x is 0, that would make this side 0, and that wouldn't happen. So x certainly cannot be 0. X can't be negative. Why is that? Well, that's from the circumstances of the problem. There's no mathematical reason why x can't be negative. But in the problem, notice that x represents a length. And a length is either 0 or positive, but never negative. So here's a restriction that's determined by the problem, not by the mathematics. Finally, this picture also suggests that x is the length of the enclosure in this direction. The side of the building is only 100 feet, and this has to butt up against it. So the largest x could be would be 100. So x has to be less than or equal to 100, also determined by the problem. Putting these all together tells us that the domain is going to be 0 to 100, 100 here, where 100 is included. So it can be 100 feet, or it can be anything bigger than 0 but not 0. So that is the domain for this function. Those are the x values that are allowed. So these are the allowable x values. And I hope that you found this problem intriguing, as I did. Viewing windows, which is most appropriate for graphing calculators, but does have bearing on computer software also. Viewing windows means that whenever you produce a graph on a piece of technology, you can only look through a given window, the window that the software or the graphing calculator allows you to look through. What we do in the way of marking this is we call this, say, the AB by CD window. Now, what is the definition here? This is considered to be the closed interval AB horizontally, and this is the closed interval CD vertically. Then the four corners are labeled by whatever points are necessary here. If this is AB and this is CD, that makes this upper point AD. The one to the right will be BD. The one to the lower left will be AC. The one to the lower right will be BC. This is horizontal first, vertical second. That's the way it's always done. Now, this is general. On calculators, what you'll find is that the A and B and the C and D that define a window actually have different terminology. So you might find, for example, this is fairly common, although every calculator is slightly different. This is common on the TI calculators. You might write X min and X max for instead of A and B by Y min and Y max. So this is the X minimum, which is this point here. This is the X maximum, this point. Y minimum, this height. And Y maximum, this height. So these seem to be very natural choices and are used fairly commonly. Now, there is the problem with a window of choosing a window. And it is important to do it well. And sometimes you can use the calculus to decide what points ought to be in the window, and sometimes you have to just use what knowledge you have of algebra. But in every case, you need to be careful what window you choose, and not always choose the window that's oriented around the origin. That may not be where the function is most interesting. Let me give you an example of what I'm looking at. Suppose we have a function like this. So it might look like something like this. And suppose we have a window, like this window that I bring up here. Now, if I look right there, the function is fairly nice and smooth. It has a nice concave up-looking figure. If I look around the origin, I see nothing at all, so I would see no graph of the function. If I look over here to the right, I find out that the function has many ups and downs that I didn't see in other windows. So depending on where you look, you are determined, what you see is determined by the window you choose. So you want to make sure that you choose a window that reflects as much of the graph as possible. And sometimes you can't do that. You'll have to take separate windows with separate scales. But that is something you want to check every time you look at choosing a window. You're probably familiar with the very useful feature of graphing calculators and software that you can zoom in and out. Well, when you zoom in and out, you have to be careful, and here are a couple of notes on that. Let's take an example here. Suppose we have the function y equals x to the fifth times x minus 2, and you'll want to look at this on your own graphing device. Let me draw two pictures now. Here is picture number 1, and here will be picture number 2. And both of them, we'll imagine, are centered on the origin. So these are windows that are centered on the origin. And both of them go from -5 to 5 in the x direction. And here is the graph of the first one. And here is the graph of the second one. Now my question is, which is the graph of y? Now they look very different. This one seems to be flat and just goes back up. This one comes down as flat and then it has a little dip below. So they're certainly different graphs. Which one would be the graph of the function y, do you think? Well, it turns out that the answer is both. They are both the graph of this function. They are simply zoomed in different ways. This first one, actually, the window is minus 5, 5 by minus 1,000, 1,000. The next one is minus 5, 5, of course, by minus 10, 10. In the first one, you zoomed out so far that you've lost all the structure in here. You're just too far away to see what's going on. In this one, you're close enough that you can see this little dip, which is completely gone here. That is the advantage and the disadvantage of zooming. You have to know enough about your function so that you don't miss out on detail like this. That's where the calculus can come in to help you find and locate this detail so that you can find a window good enough to show what you want to see. And in this case, this is a better window than this one is. But sometimes you'd actually need both because there might be features here that would disappear at this scale. So knowing that, keep in mind that zooming is something to be careful about. Finally, there's some common errors you should be aware of when you use graphing technology. Errors in resolution. One of them is, if you look at the aspect ratio, you might have a distortion. And mathematically that doesn't really matter, but psychologically it does matter. For example, suppose you're interested in graphing a circle which is centered at the origin and has radius, say, 5, just to make it large enough. If you had two pictures like this, here's the first one centered at the origin, here's another one also centered at the origin, then this is what you'd like your picture to look like, an actual circle. Here you might have this picture also, which is exactly the same thing as it turns out, except that the window is different. Minus 10 to 10 by minus 10 to 10. This is a perfectly standard window where you're going 10 units in each of the four directions, both x and y. Here, in order to get this to look like a circle, we have to change the orientation. The actual window has to be from minus 17 to 17 by minus 10 to 10. So the x distance had to be spread out a little bit in order to make this look like a circle. That's going to depend on your own calculator or the software that you're using. So sometimes, although you'll have mathematically the correct curve, it may not look like the curve you're used to because the scaling will not have the right appearance. Here's another thing that can go wrong. Pixel problems is one way to put this, nice and simply. And the problem is that pixels, especially on graphing calculators where they're so large, can leave gaps, apparent gaps, in curves. Here's what happens when you look at a screen with pixels. If you look very closely, and computer software screens, of course, is very hard to see this, but on graphing calculator screens, you can see that pixels are these little dots that make up the screen, and that's the smallest resolution that you can get. So what kind of problems happen there? Well, this is a fairly crude resolution. One problem can happen in an example like this. If we have our pixels again here, and we're trying to graph a function that has a very, very steep slant, then here's what will happen. You might get a pixel here, and one here. Now there are gaps there. There are no gaps in the actual curve you're graphing, but there are gaps in this picture. Why? Because this is also determined by the definition of a function. By the vertical line test, A function, which is what the calculator is trying to graph, a function only allows at most one pixel, which represents 1 point in the image, 1 pixel in each vertical column. Because the vertical line test has to be satisfied for a function. So if you're being slanted like this and your pixels are of these fixed sizes, what happens is in this column there's only 1 point, in this column there's only 1 point, represented by a pixel, and in this column there's only 1 point, but visually it looks like there are gaps. So you should be aware of that when you're using a grapher. Here is another thing to be aware of that often happens. Sometimes you have line segments appearing that you didn't intend. False line segments. Now there are ways to get around this, but you should know mathematically that these are not correct and be suspicious of them when you see them. So here's an example, and I'll draw both the way it should look and the way it might look if you're not careful. Suppose you have a curve that has an asymptote here, and I'll draw this so it comes out of the space so you see that that's not part of the graph. This is something I added in order to see the asymptote. What will often happen is this. The grapher will not draw this correctly like this, but will add a line in here because it's trying to connect the left and the right parts, which it shouldn't do. So this is a false line, a line that should not be there, but which the grapher will put in. So you have to know mathematically that this makes no sense. It is a nice way of representing an asymptote, but it is not part of this curve and should not be there. So you have to remember that graphers suggest correct graphs, but will often be in error. If you look too closely, if you look at the details. So use graphers wisely, understand the math.